So, good afternoon, everyone. So, in today's lecture, we are going to discuss about the technologies for network-based computing. We'll also discuss about some of the models that are system models, you can say, that are used in the field of distributed computing as well as in cloud computing. We'll see also the software environment for cloud. Like we'll discuss about the MapReduce framework. We'll see how to solve a problem using the MapReduce framework, and also we'll see related to some of the performance and energy efficiency issues related to cloud computing. So first, I'll tell you about the technologies for network-based system. So basically, this topic focuses on what are the technologies that are required whenever you want to implement a network-based system. Like you know about local area network, you know about metropolitan area network, a wide area network. We have a lot of network, right? Starting from wireless sensor network also, if you see research field, vehicular ad hoc network, you can say ad hoc network in simple. Otherwise, mobile ad hoc network, wireless sensor network, flying ad hoc network. Nowadays, we talk about unmanned aerial vehicle. These all are actually based upon, you can say, the network-based system. So when you go for network-based system, as you know that this is a completely a distributed system. So we have different type of architecture, which we generally call as the micro architecture. So here you can see there are 5 different micro architecture what you can see in today's computer systems, or our computer systems are varying with respect to their processors, and they are exploiting different type of parallelism. It may be instruction level parallelism, it may be task level parallelism. Moreover, you can say we are following nowadays, we have multi-core architecture and multi-thread architecture. So if you see overally, we can divide these micro architectures of the computer systems into 5 types. One is called as superscalar processor. Another is called as fine grain multi-threaded processor. Another is called as coarse grain multi-threaded processor. Then we have dual core processor, and we have simultaneous multi-threaded processor, which you can say in fact is one of the superior micro architecture in comparison to the earlier micro architecture. So in order to understand these 5 different architecture, you have to create some kind of threads. Like you know, thread is a lightweight process, right? We can create multiple threads so that execution of a particular program become faster. That's why we do parallelism, right? The reason of parallelism is that we can reduce the execution time by writing a parallel code. So here, if you see, we consider uh, 5 different thread. So you can see this is thread 1, thread 2, thread 3, thread 4, thread 5. So there are 5 different threads, and they are represented in the processor in different sketches, so that you can identify whether you can run multiple threads at the same time, or multiple threads one after another, or multiple threads in a single core. These different type of threads you can run with respect to the processor, that actually you can find using these 5 architecture. And in order to make a slot is not used by any thread, we represent idle slot, which is represented by a blank one, right? Or a, you can say a empty box. A empty box represents that the slot is not utilized by a particular thread. So we consider different cycles. For example, I can say, like you know, in computer we say clock cycle, right? So you can say this is 1, 2, 3, 4, 5, 6, 7, and so on. These are the different clock cycles. Okay, it may be one clock cycle per a time unit, any time unit you can consider, and in which you will see if you want to run these threads in these 5 microarchitecture, how actually they are going to process these threads in their processor. And for the simplicity of example, here we consider there are 4 functional units. So you can see this is functional unit 1, this is functional unit 2, functional unit 3, and functional unit 4. So we consider 4 different functional unit. So it may happen that one core may have one or more functional unit, right? So these functional units actually represents just like 4 different threads you can run parallelly in a particular cycle. Like in a clock, at the clock, a clock cycle 1, you can run 4 different threads at the same time, right? So if you go for 4 issue superscalar processor with 4 functional unit, so this processor actually executes single thread in 4 functional units. Like here you can see all these sketches are belongs to our thread 1. Suppose thread 1 can utilize only 3 functional unit. It is not going to execute or it is not required 4 functional unit. In that case, it is only utilizing 3 functional unit. Another functional unit is ideal. So this functional unit is actually our ideal. Now, you know that in each and every clock cycle, we are executing a set of instructions, right? We execute a set of instructions like C is equal to A plus B, which we usually write in a addition of 2-number program. That is also an instructions. If you go for assembly language, you are moving the content from the register A to register B. That is also can considered as a instructions, right? So you can see at clock cycle 1, we are executing thread 1 in 3 different functional unit. But in the next clock cycle, the requirement is for 2 functional unit. So the same thread is executing here with 2 functional unit. So what you can see in this architecture, or even if you go for the third clock cycle, we are taking these 2 functional unit and rest 2 functional units are completely ideal. So what you can get from this 4-issue superscalar processor is that we have a single thread. A single thread can occupy 1 to 4 number of functional unit. But if you are not using a functional unit, you cannot run other threads. Like if you want, let's say thread 2 to execute here, right? Because that slot is empty. Or you can say these 2 slots, which is empty in the second clock cycle. At that time, you want to execute thread 2, that is not possible in the superscalar processor, right? So that is the main drawbacks of the superscalar processor. No, it is not, you cannot say this is today's architecture. It is old architecture only, traditional architecture. But if you go for fine grain multi-threading or multi-threaded processor, so here only one instruction from the same thread you can execute. Like here you can see, here we are executing thread 1, right? So we require 3 functional units out of 4 functional units. Right? Order of these functional units are immaterial. Right? But in the next clock cycle, if you want to run another thread, that is possible. For example, here I am executing thread 1, if T1 is the representation of thread 1. In the next one, I am executing thread 3. Next one, I am executing thread number 5, and so on. So with respect to different clock cycle, okay, you can execute different threads. Okay, not necessary. You will suppose thread 1 require, let's say, 3 clock cycle. Thread 1 require 3 clock cycle to complete the works assigned to that particular thread. So you can see here we have again thread 1, right? If you notice here, here we have again thread 1. Here also we have again thread 1. So just like we have a round robin algorithm we have discussed in the previous lecture, we are giving resources to these threads one by one in a circular fashion. But at a time, a thread cannot use more than one clock cycle. That's why I told you only instructions from the same thread will be executed in each and every cycle. Right? You cannot execute multiple thread at the same time. Similarly, you cannot take multiple clock cycle to execute the instruction of the same thread. In that way, the fine-grained multi-thread processor is different from 4-issue superscalar processor. Similarly, if you go for coarse grains, there are two types of granularity also. We say one is called as fine granularity, another is coarse granularity. So if you want to understand this concept in a simpler term, you can say, suppose somebody is asking, what is your home address? Okay, you are saying, let's say, Department of CSE. Okay, address is Department of CSE. Okay, let's say room number C5. Okay, Department of CSE, NIT, Warangal. Okay, and let the pin code. Pin code is 506004. State is Telangana. Okay, and India. So if somebody is asking this address, I am telling the entire thing, okay, at the same time. So this is called as coarse granularity. Or you have a single field to enter your complete address. But if you go for fine granularity means it is much more detailed way than coarse granularity, which is represented the broader way. So if you go for fine granularity, you can say, you can ask in one field, what is your room number? Okay, you can say street address. Okay, street address. Then you can write institute name. Then you can write pin code. Let's say state name. And the last one is, let's say, country name. So in this way, if I am specifying, right, different fields to capture each and everything, that is called as our fine granularity. So obviously, fine granularity requires more memory in comparison to the coarse granularity. Okay, because you are defining the same thing in much detailed way. Obviously, it is retrieving. Suppose I want to know how many. Suppose you are entering the data of 100 different persons. Just I'll ask you, find their institute name. So it is very easy if it is fine granularity. But if you go for coarse granularity, in that case it is difficult because the entire things you captured as a single string. Okay, it is very difficult to know which one is institute name. So here you can see in the coarse granularity multi-threaded processor. Here you have many instructions from the same thread. Like here you can see, I want to execute in one clock cycle. I want to execute thread 1, but in order to complete the thread 1, I need 3 clock cycle. So, or you can say many instructions from the same thread for few cycles. Like here I am taking 2, here I am taking 3, another is 1. And at this particular point of time, means after 3 clock cycle, the thread is completed. So before switching to another thread in coarse multi-threaded processor, you have to complete the previous thread. One thread may take 3 clock cycle, another thread may take 5 clock cycle, another may take 2 clock cycle. But once you complete it, then only you can move to another thread. Like you know about other scheduling algorithms, like if you go for FCFS, so test job fast. So in that case, you are not giving different time to each and every process. Rather than you say that, let's say T1, you are deciding that first process need to execute. So until unless the first process is not completed, you will not move to process 2. But when you go for, let's say, when you go for uh, round robin type, right? Just like fine grain. You will give one clock cycle, then you will move from one thread to another thread. You'll go for another clock cycle, okay, for another thread, then you move to the next thread. Just like you will maintain a queue, and each clock cycle you are going to move from one to another. So you can simply say there is a overhead. Okay, if you look into here, that is called as a overhead, or you can say context switch overhead. Such type of overhead is there in the fine grain, which we can solve in the coarse grain multi-thread processor. Okay, so you can see once T1 is completed, I have started T3 for a couple of cycles, let's say 4 cycle. Then I have started T5 for 3 cycle. Then I started T4 another cycle. So that is called as coarse grain multi-thread, right? The next one is called as a dual core. That is called as a 2 processor CMP. Okay, CMP stands for cheap multiprocessor. Okay, so what happened here? Here we have 2 different core, right? It is a multi-core system, right? Here you can see there is a dashed line which is separating one core from another core. Now what you will do? In each and every core, you can run different thread. Okay, for a complete cycle, complete clock cycle. Like here you can see, I started thread 3 and continue, and T3 is running multiple cycle. Okay, T3 is running multiple, you can say clock cycle. Until unless it is completed, I am going to execute T3. Right? Similarly, here you can see I have started at T4, thread 4, and for a couple of cycle, it is going to execute T4. So instruction from different threads you can execute in different code, and it will, you have to provide complete clock cycle, not one clock cycle. Okay. So the advantages is that 2 different threads can run simultaneously. Till now, up to this one, up to you can say coarse grain, there is no architecture which supports that 2 different threads can be executed in each and every cycle. Right? This is the first architecture, dual core, or you can say 2 processor cheap multiprocessor, or called as CMP. This is the first architecture which provides us to execute multiple threads in a single clock cycle. You can see T3 and T4 are the 2 clock cycles that are 2 different threads executed in the same clock cycle. That is the advantages of dual core processor. 2 processing core, and each core is single threaded and 2-way superscalar processor. This is called as a 2-way superscalar processors. Right? Now the last one, last microarchitecture is another advanced one. Okay, which is used in today's system also. That is called as simultaneous multi-threaded SMT processor. Simultaneous multi-thread, or we call it SMT processor. What it enables? It enables that multiple threads, okay, or you can say instruction from different threads can be executed in the same cycle. Like if you see here, this is your thread 1, right? First one is your thread 1, second one is thread 5, this is T5, this one is thread 3, okay, and this one is thread 2. So in a single clock cycle, you have how many threads? You have 4 different threads. So you are executing 4 different threads at the same time. Okay. So it is obviously advantageous. It fulfills the demand of dual core processors also. Dual core supports by dividing into 2 different cores. Here we are not explicitly dividing into 2 cores, but we can execute multiple threads at the same time. Right? So what you can learn from here, different architectures we have, right? Although we are saying a distributed system, we can send a task or a application to an application, or application to a particular node. But if you go in the much detailed way, different type of architectures are present in different data centers. Or a data center consists of a few machines of, let's say, dual core processors, few machines of SMT processors, and other processors, and so on. Right? But if there is more blank space, right? For example, if you calculate the number of blank spaces in each and every processor, okay, these 5 processors, if there are more blank spaces, it indicates that the low scheduling efficiency. Okay, more blank space means more idle slot. More idle slot means your utilization is very poor, right? You are not properly utilizing your nodes, right, or cores. So that is shows you have lower scheduling efficiency. Okay, so these are the 5 systems. But if you want to see that it may be a CPU, it may be a GPU, right? Like I told you, cloud case we mostly they wants to achieve the power of GPU, graphical processing unit. We have CPUs also, but through GPUs you can achieve more power, right? Because GPU is having more cores in comparison to CPU, right? So if you see this uh, architecture, like today, earlier we are using MPA, today we are using CUDA programming, right? CUDA is a programming that is used for GPU programming. So if you see this GPU architecture, like here you can see, it is a simple example of a GPU that is having 16 streaming multiprocessors. If you see how many cores are there here, if you count the number of cores, here the number of cores is 8 plus 8. So total 16 streaming multi-cores. Okay. Or you can say streaming multiprocessors of 32 CUDA cores. Total number of cores is 32. Number of cores is 32. And in each and every case, you have how many cores? You have total number of cores is 16. Like if you go for a earlier machine, like there is a machine called XCEON X5670 CPU. So if you go for that, there are 6 number of cores are there. Here we are talking about 32 cores. Like if you visit top500.org website, okay, there you will find world's supercomputers, world's fastest supercomputer. There you can see the computers, the supercomputers which is listed in this top500.org site. Especially the 10 best 10 supercomputers are having some lakhs of cores. Some lakhs of cores. To imagine. Here we are talking about 32 CUDA cores, right? But there you will get some lakhs of cores. Why we are doing this one? We are doing to parallelize the program. More parallelism you can get in that case, right? That will make faster execution of the programs, right? So you can see there are different units we have. We have functional units, FP units, we have INT units. They are connected. Yeah, they are connected to the queue, right? So that whenever you want to learn a very large task, we can decompose into small tasks and we can process in the CUDA course, right? Now, you know about virtual machines, you know about the virtualization techniques. We also discussed about different type of virtualizations. Like I talked about, you can say full virtualization. We talked about partial virtualization. We discussed about para-virtualizations. These are the 3 different type of virtualizations, right? So what actually VMs, why VMs are used? VMs are the solutions to underutilized resources. If resources are not utilized, if the hardwares are not utilized, so we can create multiple VMs by the help of that particular physical hardware, so that if multiple users are using the same resources, definitely the utilization is going to be increased. That's why VMs are the solution for underutilized resources. If the application is not flexible, like earlier applications are not flexible, they can execute only in a terminal, right? They are not going to share the resources with others. You may face problem, but today's applications are very flexible. Okay, so that they can execute uh, and they can share the space of the physical machines as well. Similarly, software manageability VM is the best one. Security is also provided by the virtual machines. And overall, we call this is a single system image. I told you earlier also, single system image means user has to submit the applications and user has to get the result. And in between, number of peoples may be involved, but user don't want to go through this complexity of the environment. So for user perspective, whatever the requirement it is asked to the system needs to provide it. Whatever we have requested to a cloud service provider, our CSP needs to provide it. Okay. So there is no user don't want to know that what is the complexity of the environment, how many VMs are there, how they are connected to each other, right? That's why for the user perspective, the entire system is treated as a single system. So here you can see there are three types of VM architecture. One is called as a native virtual machine, another is called as hosted virtual machine, another is called as a dual mode virtual machine. Like we have discussed now about dual core chief multiprocessor, right? Similarly, here we have dual mode virtual machines. So you see here in the physical machine, we have hardware. On top of the hardware, we have operating system. Operating system is interacting with the user and computer hardware. And on top of the operating system, you are deploying applications. So there are two modes we considered here. One is called as a privileged mode. Another is called as non-privileged mode. Like, the entire space is divided into user space. Another is called as your kernel space or system space. User have no right to enter to the kernel space. Okay. Something you can modify, that to be the super user can modify. And privileged mode means you can make modifications. Right? This is a non-privileged mode in the user space and privileged mode in the system space. Okay. Whether a mode is privileged or not, that depends upon the different types of user, whether the permission is given to or not. Like we can say privilege is nothing but a special right that you have given to a person. Right. But when you go for instead of physical machine, if I go for a native virtual machine, in native virtual machine, what happens? So on top of hardware, we have hypervisor or virtual machine monitor. And on top of virtual machine monitor, you can install a guest operating system. So this VMM is in the privilege mode. It is a system mode. But guest operating system is in the user space. Right? So you can see this line separates the user space to the system space. And on top of the guest operating system, you can launch different type of applications. Right? Now, if you move from native virtual machine to the hosted virtual machine, we have hardware and we have host operating system. The difference between these two architecture you can see that is both are belongs to the full virtualization. But the main difference between these two is that second case, this hosted virtual machine case, host operating system is there. But native virtual machine case, there is no need of any host operating system. Whereas another difference you can also say, here VMM is running in privileged mode, but here VMM is running in non-privileged mode. So on top of VMM, you can install the guest operating systems or guest applications. But it is on top of the VMM is on top of host operating system. If host operating system is there to launch the guest operating system by the help of VMM, we call that as a hosted virtual machine. But if there is no need of any host operating system, then we call that as a native virtual machines. So in order to compensate this gap, these are two, you can again say these are two different type of technologies that are used in VM, like para virtualization, partial virtualization, full virtualization. It purely depends on whether your hardware, computer hardware supports it or not. That's why another architecture is called as a dual mode VM. What we have in dual mode VM? Here you can see BMM is a part of both privileged mode as well as non-privileged mode, or you can say user space as a also part of system space, right? And on top of BMM, you can go for guest operating system and guest applications. And you have also host operating system like hosted virtual machine. Okay, so these are the basic difference between these three virtual machine architecture, and it is different from our physical machines. And here, multiple users can use the resources, whereas in the physical machine, only one user can use the resources. That is the only difference between the physical machine and VM-based architecture. Yeah, here you can see native virtual machine case. What we have seen, VMM and hypervisor. VMM or hypervisor in the privileged mode. Okay. So hypervisor it actually handles the bare hardware, that is CPU, memory, and I/O. It creates the virtual machine, monitors the virtual machine. And hosted VM case we have seen there is no. You can say in the previous case there is no host operating system, but in this case we have host operating system. But as it is in privileged mode, user cannot modify it. Privilege means permission. Privileged mode for which one? System space. Privileged mode is not for the user. So user cannot modify it, right? And VMM in the non-privileged. As VMM is the non-privileged mode, so that is your user space. When you go for dual mode virtual machine, one part we have seen in the user level, another part is there in the system level, or you can say supervisor level. But as host operating system is there, you can say host operating system is there in the privileged mode, but VMM is there in the both mode, and VMM can also deal with the CPU, memory, and I/O, so it can be modified. It may be or modified, right? Okay, like that we have four different architectures, and you can do a couple of operations by the help of VM virtual machines. Like here you can see uh, there are four different concepts you can look into the virtual machines by the help of virtual machine. First one is called as multiplexing. So in the multiplexing case, what we have? We have storage. On top of the storage, we have hardware, right? Let's say I'm taking a part of the storage. I want to create some virtual machine. I'm taking another part and I'm building another set of virtual machines. So on top of the hardware, we have VMM, right? And on top of VMM, you can go for multiple guest operating system. These are guest operating system. And you can see in this architecture, we don't have any host operating system. As there is no host operating system, you can claim this is called as your native virtual machine. Okay. So you have two virtual machines. One is virtual machine 1, virtual machine 2. And these two virtual machines are taking the resources of the physical machines. Right? So the same hardware we are providing to virtual machine 1 as well as to virtual machine 2. But suppose you have started a particular company. You have taken instances from Amazon EC2, right? Later point of time, you have seen there are many requests reaching to your site. So you want to expand your infrastructure. Let's say you have taken a small instance. Now you want to move to a medium or large instance. So, but if I want to expand the resources of this virtual machine, then it is not fitting with this hardware. Okay. Like suppose some your hardware supports, let's say 16 GB. You have created two virtual machines. Let's say one is 6 GB, another is 6 GB. You want to expand from 6 GB to another 6 GB. But whole total, we have how many GBs? 18 GBs. So 18 GB cannot be satisfied by this hardware. So what you have to do? You have to stop this particular virtual machine, okay? And you have to keep in this storage, because you have to find a destination host. This is your source host. This is your source host. But as you want to expand, source host is not capable to handle it. So what happened? In that case, you have to look for a destination host. But if the destination host cannot be decided immediately, then you have to move, you have to create the image of this virtual machine, and you have to store in the storage, right? And you go on finding the destination host. Like you can ask this host if any other host is there. You can think that which host is suitable for this particular virtual machine. Suppose you found that you can launch this virtual machine which we have suspended, that is VM1, in this hardware. On top of this hardware, you can uh, resume the work of this particular virtual machines. So what happened? You have suspended here. Here the process we have seen, that is called as multiplexing. Multiplexing means, multiple signal is sent over a single channel. In data communication we have studied. There are multiple channels, but you want to share through a single channel. Here we have suspended the virtual machines. Right? Virtual machine is suspended and stored in a place. Right? Again, we need to provision. We need to resume the work. So we have launched here, and we can start the execution of this particular version from that point onwards. Right? As you have created the image file, you can resume the work from that point onwards. Right? Or this is a concept of checkpointing. Okay, your result is stored, so you can resume the work from that point onwards. But here you can see in the process of the suspension and provision, it takes time. Suspending a particular version like EC2, we have seen, we have terminated the instances or suspended the instances, but it takes some little bit time to remove the instances from the Amazon server, right? So this type of migrations are actually called as a cold migration, right? Because you have to wait, it requires a little bit of time or move from one host to another host. But through live migration, if you go for the process of live migration, so in that case, once you decide that, let's say this virtual machine, I want to migrate from this hardware to this hardware. Okay, I want to migrate from one hardware to another hardware. So without suspending this particular virtual machine, storing in the storage, again resume the work here, you can directly do it. That process is called as a live migration. Right? Without any interruptions, you can resume the work on top of another hardware system. Okay? So that is the advantages, right, of the live migration, where there is no delay. Even if there is a delay, that is negligible. But in this case, there is a huge time is required to suspend the virtual machine, again to resume the work, find the destination host before resuming the work. It takes a lot of time. Okay. Now you can see sometimes the resources are not sufficient. Like we have a physical network, we want to create a virtual network. Like if you take two organizations, organization A and organization B. Organization A is having, let's say, 20 server. Organization B is having 10 server. Okay. But in order to execute an application X, what you need? Application X, you need 25 servers. So first you have approach to A. A cannot fulfill it because the number of process resources is 25, but you have only 20. B also cannot satisfy because 25 is quite more in comparison to 10. So you can visualize this 20 and 10 is just like this physical links. Number of computer systems or number of nodes are connected to each other, okay, through different routers. Also, they are connected to an access point, right? But if both organizations collaborate together, like we are talking about multiple cloud, okay, in that case, one cloud service provider need to collaborate with the other cloud service provider in order to provide the service, right? One cloud service provider need to collaborate with other service provider. This collaboration can happen between public clouds, may happen between private cloud also. Sometimes it may be combination of public private cloud also. We can also visualize that is a hybrid cloud. So if these both organization collaborate together they have 30 different servers. So if they collaborate, then application X can be executed because application X requires only 25 servers. Okay, and together they have 30 servers. So it is sufficient for them for that particular application to execute. So what they actually doing? They are creating a virtual infrastructure, right? So simply we call this is a overlay network. The actual network is called as IP network. Right? Underlying network is, if there is a overlay network is virtual, underlay network you have IP network, the physical network. So suppose I want to take only subset, like I don't want to take all 20s or 10. I want to take, let's say, 18 from here. Okay, 18 from here, right? I want to take, let's say, 7 from here. So together we have 25 servers. So let's say I'm connecting like this. Okay, you can see we have connected, we have created the virtual link, and we can run the application in the overlay network. Okay, overlay network is providing a virtual infrastructure to uh, execute an application by collaborating multiple organizations. So here each and every node can be act as a client or it may be server. They can join and leave at any point of time, but at the same time you can see that it should not be below 25. Okay, can also suppose they need another server. Okay, there is another 2 remaining here, another 3 remaining here, right? So at any point of time you have to look into the number of servers is not below 25 in the overlay network. So in this overlay network you can see there is no master slave relationship and there is no coordination or central database to deal with it. So that's why it is providing a better infrastructure to execute applications when there is a resource requirement is more and availability is less for a particular organizations. So we can say through this peer-to-peer network, cloud is also a part of this peer-to-peer network. So in that case, we can make a 2 abstraction level to deal with such type of problem. So here, yes, as I said, one is physical network, another is called as overlay network. So physical networks are the ad hoc network. Ad hoc network is temporary network. So they are connected through TCP/IP or network access identifier protocol. Obviously, its size and topology varies dynamically because anybody can join and leave at the same time. If you look into BONC platform also, Berkeley Open System for Network Computing, in this platform also, anybody can join, anybody can leave at any point of time. That's why in that sense, we say that is a ad hoc network, right? So, but you have to ensure that in order to execute a particular work, sufficient machines are becomes available. That's why we are going for overlay network. Not only 2 organizations, multiple organizations under different administrative domain, different time zones can be associated together to provide the resources to a particular applications. So we map the physical machines with IDs. Each and every physical machine with ID so that we can know that whether a particular machine is active or it has left the network. So whenever a new peer is joined, whenever a new node is joining, a peer ID is added. So that I should know, right, how many machines are active at the same time. Like if you go for a project that is source for extraterrestrial intelligence at home, in this project you will see some lakhs of machines. Even if many people are joining or many people are leaving from the network, in each and every sign you can see more than lakhs of machines are active to provide supports to the computational requirement, right? So whenever a peer joins, you have to add you have to give a ID and you will say that number of nodes are increased by 1. And whenever a peer is leaves, you have to simply remove one of the number of peers, right? Out of the number of peers, you have to deduct it by 1. Okay, so this overlay network is again 2 types. It may be structured Like when you go for routing protocols, you can observe the topology, and based upon that, you can find a path between source to the destination. Or if it is not structured, it is unstructured. Unstructured is similar to a random graph. There is no peculiarity in that particular graph. There is no fixed route. If you have followed a particular path from source to destination, in the next sequence, the path is again different. So in that case, we are going for message flooding. Each and every node has to flood the message to different nodes in order to establish a particular path. Okay, sometimes these results are non-deterministic, search results are non-deterministic. Sometimes also we don't know that there may be a heavy network traffic also, right? So there are a lot of issues if it is having a unstructured network, right? Like that, different types of system models we have. Some system models assume that all the resources are homogeneous in nature. Sometimes we assume that the resources are heterogeneous in nature, right? Sometimes we consider different types of systems. Like one CSP is more capable, having more data centers. Another CSP is having less data centers. So in that way, we can consider different system models for distributed computing as well as in the cloud computing. Now, let us see the software environment. Which software environment is used for distributed system in cloud? Earlier, I already told you one is message passing interface is a very popular platform that is used in the case of as a software environment. You can write the code in MPI. You can also use parallel virtual machine PVM. Okay, it also supports you to write the machine. Like that, there are number of you can say examples you can find to write code if you want to connect two different systems. You can use these systems to interact with each other or share the resources with each other. A number of softwares we have, right? One of the another popular software is called as MapReduce. Okay, that is a very popular model. It is in fact a web programming model for you can say data processing, like big data case we are using. Okay, if you want to process any data and if you have a very large cluster and you have a very large data set, like big data, we are dealing with very large data sets. So in that case, MapReduce is a very popular platform. You can go for Hadoop also. Hadoop is also a software library. You can write and run large user application and deal with very vast data sets. In generally, business applications are dealing with very large data sets. In that case, you can also go for Hadoop. So let us more focus on this model, that is MapReduce framework. So in the MapReduce framework, you have a function called map. You have a function called map. Map function actually generates a set of intermediate key and value pair. The main purpose of using a map function is to go for key and value pairs. I'll tell you with an example what is the meaning of this key and value pairs. And there is another function that is called the reduce. Okay. And this function is responsible to merge all intermediate values with the same key. Okay, some key is there with one reduce function, some key is there with another reduce function. So our objective in the reduce function is to merge all such intermediate values with the same key. Another simple architecture you can find here, like you are giving a very large input file as input to MapReduce. Okay. We have to provide a large set of files. Okay, I'll give an example with simple set of files, but you can think of very large files. Okay, then the input is going to be divided, right? For example, I have three map function here, right? You can say is the first function, is the second function, is the third function. So I have to divide the input into three different chunks. Because I told you map function is there to generate the key value pair. Before generating key value pair, you have to give the data to each and every map function, right? That's why each and every map function is going to take a piece of data. So you have to split the data into multiple parts. For example, assume that you have a text file. In that text file, you have number of sentences. Let's say number of sentences 12. I'm giving a random example, 12. I have three map functions. Okay, so what I'll do, I'll give each and every map function with 4 different lines, right? So that this map function can generate a set of intermediate key and value pairs. Okay. Now, once map function is done, so this is this division of the data, input data into different part is called as splitting. First input is given, you have to divide into small chunks, right? Not necessarily 3 map function. You can take as many number of as map function possible. Okay. So the process of dividing the input is called as splitting. Once splitting is done, what we are doing? We are going for the process of mapping. So you can see there are different type of mappers are there through which we can generate the key value pair. Once you get the key value pair, before going to this reduce page, we are using a process that is called as shuffling. We have to shuffle it, right? Because you may get some result in this map function with respect to a key value pair. You may get different value here, different value here. Again, you have to, before to reduce it, you have to arrange them. That is called as the process of shuffling. Then after shuffling, you are applying the process of reducing. Reducing will consolidate the shuffling values. Right? Then you will generate these values are again reduced to a single file, and finally the output is generated. These are the simple steps followed by the MapReduce program. Okay, now let us see a small example to understand this MapReduce process, right? One of the very popular example for MapReduce is the word count process. Okay, word count process means you are given with a text file. You have to count. Okay, you have to count number of occurrence of each and every word, right? Occurrences of each and every word that you have to determine. For example, if you see this example, here I have given 3 different sentences, right? One is deer, beer, and river. Another is car, river. Another is deer, car, beer, right? So these are the 3 different sentences you have given in a text file. What is your output? Output is the occurrences of each and every word. So let me write here how many times D is repeated. Let us represent it by first letter. How many times B is repeated? How many times R is repeated? How many times C is repeated? Okay. So you can see D is repeated here. D is again repeated here. So the occurrence of D is 2. B is repeated here. B is also repeated here. So its occurrence is 2. R is repeated here. R is repeated here. So its recurrence is 2. C is repeated here as well as here. So its occurrence is 3. So if an input file is given like this, you have to produce an output like this by the process of MapReduce. This example may be a simple one, but whenever you go for the MapReduce, actually writing the code, okay, you will see you have to deal with very large files, not small files. You have to deal with large files. So what I can do here, First is called as the process of splitting. Splitting means it says that you have to divide the file into number of chunks. Like, let us take an illustration with the three different map functions. So I can say the first line will give into the first map function, second line to the second map function, and third line to the third map function. Okay, first line I'll give to the first map function, second to the second function, third to the third function. So we have split it into three different parts. And you have to split more or less the each and every part need to be equal. Okay, if you are dealing with a 10 GB data and you have 10 different map functions, so you have to ensure that in each and every map function you have 1 GB of data. Okay, otherwise one map function may get more data, one is getting less data. That is not good. It is again having a balancing issues, right? Now, once the process of splitting is done, then that is given input to the mapping function. I already mentioned mapping function means it is going to produce what? Key value pair. So this K indicates your key, B indicates your value. So it is counting occurrences of each and every word. D is repeated one time, B is repeated one time, R is repeated one time. Right? Similarly, in this sentence, if you go for the map 2, second map function, C is repeated one time, C is repeated another time, R is repeated another time. Last one, D is repeated one time, C is repeated one time, B is repeated one time. That's why I told you map function's role is to generate this set of key and value pair. But again, there should be a unit who, as I said, D, a word is starting from D, another is from B, R, and C, right? So each and these D, B, R, C, one unit should be responsible to count the number of Ds in each and every mapper. Another unit is required to count the number of occurrence of B, or another unit is required to count the occurrence of R and C, or combining RC and combining DB. So here you can see this unit I am calculating the B, right? Here in the suppling process, I am only calculating B value here. Okay, so those units are having the occurrences of B. Okay, in the mapping phase, those mappers are having the occurrences of B. They have to give the count value to this unit. So you can see here one B is there, here one B is there. So both units are connected to here. So here we are counting 1, 1 in the suppling process. Similarly, here, if you look into this car, right? Here we don't have any car, right? So this map 1 is not connected to car. But here we have two occurrences. So you can see two ones. Here also we have one occurrences. So we have one. Similarly, this unit is responsible for D. So D is one time here, D is one time here. So 1, 1. Similarly, we have R one time here, R one time here, right? So if I calculate now, how many times each and every word is repeated? Just we have note down that what is the occurrences. Like here, every occurrence is 1. That's why you are not able to identify. Sometimes the occurrence may be in one unit is more than 1 also. Like here you can see more than it is 2. So you can write car 2, 1 also. Right? So what reducing unit is going to do? It is consolidating it. I told you merge all intermediate values with the same key. So these are the with the same key multiple occurrences. So it is 2. Okay, here 3 times, here 2 times, here 2 times. So reducing after merging it again, the final result is determined by merging all the occurrences of each and every word. So you will return B is 2 times, C is 3 times, D is 2 times, and R is 2 times. Okay. So in this way, actually, the map reduce framework works. So now if I give a new example, okay, for example, Suppose there is another example which is available in public domain that it says, welcome to Hadoop. Welcome to Hadoop. Class Hadoop is good. Hadoop is, let's say, bad. So this is the text file for a simplicity of example. Can you split it by the same process by applying the process of, let me write here. First, you have to apply the process of splitting, as I said earlier. Then perform the process of mapping. Then go for the process of shuffling. Then go for the process of reducing. Then produce the final result. Can you please try this example? You can take a snapshot of this example. Let me clear it. Yeah. You clear the snapshot of this example. Take a snapshot of this example and solve by taking this file. Welcome to Hadoop. The class Hadoop is and good Hadoop is bad. You take this file as input. Then see, show the steps in the splitting, mapping, shuffling, reducing, and final result steps. Please do it. Let us split it into three parts like previous one so that we can get the same result. Split it into three parts, and based upon the number of words, you can choose the number of reduce function. Do it. So what you will take first in the splitting phase? Can anybody tell? First, what you will take in the split phase? You have to take three different parts. What are the parts you will take? First part is which one is your first part? If you split it into three parts, please respond. Okay, first part you have to take welcome to Hadoop, right? So one part you write welcome to Hadoop. This is your first part. Okay. Second part you take class Hadoop is. That is your second part. Third part is, let's say, good Hadoop is bad. Right? Just randomly I'm taking. Okay, you can split in different ways also. Now it is split into three parts. What we will do in the welcome page, that mapping page, welcome is repeated how many times? One time. The count of welcome is one. Two is again one time. Hadoop is again one time. This we got here. Class is one time. Hadoop is one time. Is one time. It is done. Next is good is one time. Hadoop is one time. Is one time. And bad is one time. Right? We have taken individual occurrences. Right? Now, when you go for shuffle, okay, shuffling case, what you have to do for each and every word, you have to take one. right? For example, I can take, for example, I'm taking bed. So bed is occurred how many times? Is there any bed here? No. Any bed word here? No. Here it is there. So it is connected to this one. So it will say bed is repeated one time. Let's say I'm taking class. Okay. Is there any class here? No. Is there any class here? Yes. So I'm connecting this to class is repeated one time. There is no class here. Similarly, I'm taking good. There is no word good in the first one. There is no word good in the second one. There is a good in the third one. Okay. Then suppose I'll take Hadoop. Next word is Hadoop. So Hadoop, you can find here it is one time. Here also it occurs one time. Here also it occurs one time. Right? Then if you go for each is here one time, here one time. So 1, 1. Then if you go for 2 is occurred only one time here. Right? And the last one, let's say welcome. Welcome is occurred only one time here. Right? This is the suppling phase. Now, in the reduce phase, what you have to do? This one time. Class is repeated only one time. Its occurrence is 1. Word count. Good is equal to 1. Hadoop is 3 times. Is repeated 2 times. And 2 is repeated 1 time. And welcome is repeated 1 time. Okay. So in the final result, you have to merge all. Like bed is 1 time, class is repeated 1 time, good is also repeated 1 time, Hadoop is 3 times, each is 2 times, 2 is 1 time, welcome in 1 time. You may get different order also, there is no issue. Right? This is the final output you will get. Okay, given a particular file, you have to deal like this when you go for MapReduce. Right? Now the last part we'll discuss, that is called as performance. So in order to calculate the performance of the system, so there are different laws we have. One of the very popular law is called as Amdahl's law. Okay. So we'll see through Amdahl's law how you can derive and you can also see that how to deal whether a particular if a code is given to you and you can assume that in that code how many lines you can execute in parallel and how many lines it is sequential. Based upon that, you can do some kind of analysis. So we have two laws. One is Amdahl's law, another is called as that Gustafson's law. So these two laws we'll see so that you can compare that if a system is there with a parallel, some codes are parallel codes and some codes are sequential, then what is their factor, speed of factor, or what is the importance, whether we need to increase the number of resources or not, that you can decide. So in order to understand this Amdahl's law, let us consider a program. Okay, and this program is already given to you, and this program you want to execute in a uniprocessor workstations. Let's say you have a computer system, and that computer system is having only one processor, and the total execution time of 3 minutes. If you want to execute a uniprocessor, execute your workload in a uniprocessor workstations, it takes a execution time of 3 minutes, right? But let's assume that the program is parallelized one. If it is a sequential, it's okay. It is taking 3 minutes of time. You have a program P, you want to execute in a workstation W, so it is taking T unit of time, anytime. So here we consider the time unit is t minutes. The program can also be parallelized. All the lines are not sequential, right? Some lines are sequential, some lines are parallel, right? So let us assume that alpha, fraction of alpha, whatever program you have written, part of the program alpha of the code must be executed sequentially, right? So you cannot run it parallel. Like you have written some code, up to this, it is sequential. Then after that, you have written, let's say, some kind of loop, okay, where you want to do multiple works and they are not independent, they are not dependent on each other. Let's say you have written a procedure that is not dependent on each other. So the fraction alpha of the code is executed sequentially, and the remaining code, if the total code I can consider as 1, so rest code is 1 minus alpha. Okay, rest code is 1 minus alpha. So 1 minus alpha of the code can be compiled parallel execution with n number of processors. Okay, so if you consider the total code is 1, in this total code 1, alpha code is sequential. 1 minus alpha code is parallel. So if the code is sequential, you need only one processor, right? But if the code is parallel, then if you have more than one processor, you can divide the workload among them. And you know what is the total execution time of the program. Total execution time, you know, t minutes. So this alpha into t, if you calculate the total execution time, alpha into t, and 1 minus alpha code is sequential, 1 minus alpha code is parallel. So in order to execute this one, it is also taking t minutes of time. It is also t minutes of time. But if it can be executed as it is parallel and you have n processor, so this time can be divided by n, right? So alpha into t, this is for sequential, and 1 minus alpha is for parallel. Here I divided by n because we consider n number of processors, right? Sequential is alpha t, parallel is 1 minus alpha t by n. But not only this, the complete system. Sometimes there are different type of overheads we have, like we have system overhead. We are communicating from one unit to another unit, that is causes the communication overhead also. Okay, one processor is communicating with another processor. This processor is calculating, let's say C is equal to A plus B, and C minus A is equal to D is calculated by processor P2. Right. So P2 can only execute if you provide the value of C. So there is a communication between P1 and P2. So this is also an overhead. P2 has to wait until unless P1 provides that particular value. So such type of overhead we have ignored here. Sometimes user is giving input, that is called as input output overhead. Sometimes there is abnormal things can occur in your program. It may create some kind of exceptions. Okay, such times also takes time or not? They are also taking time. So that also we have not included while considering this law. Now, if I ask you to calculate the speed of factor, okay, speed of factor, the total code is alpha is sequential, 1 minus alpha is parallel. So total code is alpha is cancelled, it is 1. So if the entire code is sequential, it is going to take t unit of time. That we can say non-pipelined processor. Okay. So speed of factor, while you are calculating, you have to compare the performance of a non-pipelined processor against a pipelined processor. Right. So speed up factor of using n processor system over a single processor system. If it is single processor system, it is taking t unit of time. There is no alpha code is parallel, 1 minus alpha code is alpha code is sequential, 1 minus alpha code is parallel. Whether it is sequential or parallel, as there is a single processor, you have to execute it. So it is one only. The total code is one. It takes a t time to execute. But if the code is alpha code is sequential, 1 minus alpha code is parallel, then it is alpha t plus 1 minus alpha t divided by n, which we have seen in the previous slide. Alpha t code is for the sequential, 1 minus alpha t by n is for parallel. If it is an n processor system, but a single processor system, it is t. So here also you have t in the denominator. If you take common, t divided by, if I take t common, alpha plus 1 minus alpha by n. So this t and t can be cancelled out. So you can write 1 by alpha plus 1 minus alpha by n. Right? So t can be cancelled out. Both are taking t unit of time, so there is no need to consider. Okay, if it is sequential, like here sequential parallel is same, right? Sequential parallel, there is no concept of sequential parallel because it is a single process system. That's why it is one. But here, part of the code is sequential, rest of the code is parallel. So 1 minus alpha divided by n. So sequential bottleneck says that alpha is equal to 0. Okay, let. So code is parallelizable. If alpha is equal to 0, this represents sequential, right? This alpha represents sequential. 1 minus alpha represents parallel. Right? 1 minus alpha is represents parallel. Sequential bottleneck means what? Alpha is equal to 0. Means whole code is parallelizable. Whole code is parallelizable. Means total code is 1 divided by n. Okay. So if alpha is equal to 0, so it is 1 by 0 plus 1 minus 0 by n. Okay. So how much you will get? 1, if you do it, 1 divided by 1 by n. So it is equal to n. Right or no? You see how the entire expression is reduced to n. So when you deal with a large number of clusters, generally we deal with large number of clusters. The backbone of cloud is only the clusters and grids. So when we deal with a large number of clusters, the n value is very high. N is nothing but your number of processors is very high. So if number of processor is very high, let's say tends to infinity, right? Tends to infinity because it is a very large one. Number of n is not a small number like 2, 3. It is a very large number. So n tends to infinity. If n is very large, then you can consider n is infinity. So here the speed of actually approaches to 1 by alpha. That is our upper bound. Okay, like here you can see this alpha value, right? If the entire code is, let's say, parallel. Entire code is parallel means you will get 1 by n. The total code is, if it is 1, n number of processes are there to execute, it is 1 by n. So if you look into this calculation, what it says, s approaches to 1 by alpha. And surprisingly, this upper bound is independent of the cluster size n because there is no n value here. If I say s determines, okay, let's say n by alpha. So it is dependent on n, right? But if s determines 1 by alpha, so it is independent of the cluster size n. So whether your n size is very large or small, it is not going to depend upon that. Let us take a small calculation to understand these things in more better way. Let's say alpha is equal to 0.25. You have written a program P, 25% of the code is sequential. 0.25 or 25% of the code is sequential. Rest code is parallel. This code is 0.75 is parallel. Right? And let's say number of systems is equal to, we'll take a case with 1. Assume that you have a cluster. The cluster contains only one node, means one workstation. This is your scenario 1. In scenario 2, let us consider a cluster that is having 100 different nodes, right? So, speed of S is equal to 1 by alpha plus 1 minus alpha by n. So, if I put these values here by considering scenario S1, so 1 divided by alpha is 0.25. 1 minus alpha is 0.75 divided by n. N is 1, right or no? So, how much you will get? 1 divided by, this is also 1, equal to 1. So, in the scenario 1 case, where the number of nodes is equal to 1, it is 1 only. Okay, that means you are dealing with a single process system. You don't have multi-process system. That's why it is coming as 1. But if I go for scenario 2, let us go for scenario 2. In scenario 2, if you see, S is equal to 1 by alpha plus 1 minus alpha by n, right? So, it is equal to 1 by, what is the alpha value? Alpha value is 0.25. 1 by minus alpha value is 0.75. Divided by number of nodes is equal to 100. Two scenario, right? First scenario is you have taken 1 divided by 1. But here I have taken 100. So how much it will come? 1 by, if you do it, can anybody calculate and tell me? 1 by 0.25 plus 0.75 divided by 100. How much you will get? 3.88 you are getting, right? So what actually you have to do? 0.25 plus this 0.75 by 100. Okay, 0.75 divided by 100. I think you will get something as equal to how much you are getting? 0.75 divided by 100. 0.0075. You add 0.25 with that, okay? So it is 1 by 0.257. And if you divide it, you are getting 3.88. Yes, you're correct. So what it says, if you deal with only one system, your speed up is 1. Speed up means pipeline processor to non-pipeline processor. But if you increase the number of node to 1000, sorry, number of node to 100, not 1000, 100, the speed up value is increased to only 3.88. With one system, speed up is 1. With 100 systems, the speed up value is 3.88. So if you take 1000 also, let us try with 1000. 1 by 0.25 plus 0.75 divided by 1000. So 0.75 divided by 1000. How much you will get it? 0.00075 plus 0.25. So 1 divided by 0.25075. 1 divided by 0.25075. How much you are getting? You are getting 3.98. Yeah, you're correct, meaning. So what is the conclusion here? The conclusion is that if we increase the number of processor, the speed up is not increasing. That's why while discussing the workflow scheduling, I also told you, whenever you are generating the workflow, you have to give input the number of tasks, width and depth. If width of the graph is very small, then increasing the number of processor greater than the width value is not going to increase the performance. Okay. That's why it says that increasing the cluster size alone is not going to increase the speed of value. Okay, that is the main observation. Another observation is that it is a sequential bottleneck where alpha is equal to 0. Okay, so this value should be as low as small as possible. Sequential bottleneck should be as less as possible. If the code is parallelizable, then only you can take advantages. If the code is sequential, that is not going to give you more benefit, right? So there are some problem when you deal with fixed workload. Like Amdahl's law, what we discussed here, that is speed of S is equal to 1 divided by alpha plus 1 minus alpha divided by n. So it works for only the fixed workload speed up. The program is there, okay, and alpha and 1 minus alpha is there, that is sequential and parallel, and the workload is fixed. There you can only apply Amdahl's law. To execute a fixed workload like Amdahl's law on n processor, suppose in your system you have n processor, you want to execute the fixed workload. So parallel processing may lead to a system efficiency. Remember, S is equal to this formula, E is equal to efficiency can be calculated S by N. Like here you have calculated the speed of factor S, right? So if I ask you to calculate the efficiency, so you have to do efficiency divided by S by N. So what is the efficiency here? S is equal to 1 divided by 1. So you will get 1. Efficiency is 1. In the second case, where you have taken 100 node, efficiency is equal to S by N. So S you got as 3.88 divided by N. N is equal to 256. Sorry, what is the N value here? 100. So you will get efficiency is how much you are getting? Is low, right? That is efficiency is only 0.0388, right? It is very low. So in order to calculate efficiency, you have to divide the speed up factor by N. So what I will do here, so if you put this here, S value here, 1 by alpha plus 1 minus alpha by N divided by N. Okay, by divided by N, right? Is it divided by 1 N or not, right? I am only putting S value here. So what you will get here is divided by N is multiplied by 1 by N. So I can write 1 by N alpha plus 1 minus alpha. It is divided here. So you have to write in multiplied by 1 by N. So I am multiplying N term here, N term here. So N will be cancelled out. So you will get N alpha plus 1 by 1 minus alpha. Now, if I consider the number of nodes is 256, earlier example you have taken N is equal to 1, N is equal to 100. So it is 1 by number of nodes is 256 multiplied by alpha is 0.25. Okay. In this case, they have taken alpha n. Okay, I am taking n alpha. Okay, you can do either way because it is a into b is b equal to a, b into a. 1 minus alpha is 0.75. So if you solve this one, 256 into 0.25, 256 into 0.25, that is 64, right? Plus 0.75. So 64.75. And 1 divided by 64.75 will give you 0.01544, which is equal to 1.5%. So what you can say? Low efficiency. Why it is low efficiency? As the speed up is equal to 3.88, or if you take ceiling function, it is 4. If you take ceil, it is 4 or not. So it is only making 4 processors busy. But other processors means 256 minus 4 is 252 number of processors are completely idle. As these many processors are completely idle, so we are getting efficiency as only 1.5%. Okay, that's why you need to see that how to increase the speed of value. And based upon the speed of value, you have to choose the number of processors. Okay, otherwise that is of no use. So another one is when you move from fixed workload to a scaled workload, you have to go for another law which was developed in 1988. It is a very famous law that is called as Gustafson law. Okay. So here let us consider W is the workload in a given program. Okay, W is the workload in a program. So I just want to write here what is the speed of value again, so that you can see all the formulas associated with each other. Alpha plus 1 minus alpha divided by n. Okay. And what is efficiency? Efficiency is nothing but 1 by alpha n plus 1 minus alpha. Okay. Now, if you consider n processor system, so the workload is W, right? If it is sequential or parallel, the workload is W only. Here you can consider n number of processors, or you can consider a single process. So only the parallelizable portion of the workload is scaled n times in the second term. Okay, the workload of each and every system is W. So if I am taking n different system into consideration, then it is n W. That's why n times it is multiplied. And W days is the sequential execution time on a single processor. If it is a single processor, it is going to take alpha W. Single processor means alpha W plus 1 minus alpha NW. What happens if it is a parallel process? Parallel processor case, it will take only W. Okay. So if you calculate speed of S days, because previous case you have taken S, that's why it's S days here. And here if you take W as common from the numerator, so it is alpha plus 1 minus alpha into n divided by W. So W will be cancelled out. So it is alpha plus 1 minus alpha n. Right? Now, if I ask you to go for efficiency, efficiency E days is nothing but S days divided by n. S days you have calculated as alpha plus 1 minus alpha n divided by n. So if I multiply n in both the term, okay. So S days you got, right? N. Then what will happen? This is if I divide it by n. So alpha plus 1 minus alpha n divided by n and n divided by n. So how much you will get here? It is alpha divided by n plus 1 minus alpha divided by 1 means it is equal to alpha n plus 1 minus alpha. So by fixing the parallel execution time at level W, the efficiency you can calculate it like this. Now let us take an example so that you can see that what is the difference between a fixed workload and a scaled workload. So what you got here? You got here E days is nothing but alpha divided by n plus 1 minus alpha. Right? You can see here whatever I have written here. Whereas how to calculate the speed up? The speed up can be calculated here as alpha plus 1 minus alpha n is equal to speed up. Now, if the number of nodes is 256, okay, if number of nodes is 256, so n value you know 256, right or not? And let's say 0.25 code is sequential and 0.75 code is parallel. So what I can do? Alpha is your 0.25, right? 1 minus alpha is your 0.75 multiplied by n. N is let's say 256. That will give you the speed up. Okay, how much you are getting speed up? Can anybody calculate and tell me? 0.75 into 256, because the number of nodes is given as 256 in your cluster. Okay, so it will give you 192.25 if I'm correct. Right, 192.25. If you calculate E days, okay, what is E days you will get? So it is simply, you have to, what you have to do? You have to divide it by n. So you'll get either you do it S days by n. So that is 192.25 divided by 256. You will get the value as 0.7509, which is equivalent to 0.751. Or you can directly put here if you calculate efficiency. E days is equal to alpha. Alpha is 0.25 divided by n. N is 256 plus 1 minus alpha is 0.75. So 0.25 divided by 256, okay, plus 0.75. So it is 0.7509 or equivalent to 0.751. Both way you can do it. Either calculate the speed up factor, divided it by n, or you can directly put in this formula. So you can see what is the efficiency. Efficiency is now 75%. Because speed up is 192, that means you can utilize as many as 192 or 193 number of processors. You try this example again. E days is equal to alpha n plus 1 minus alpha. You try with 193. So 0.25 divided by, let's say, 193 plus 0.75. Can anybody calculate and tell me? 0.25, how much you are getting? 75. So 75% you are utilizing. Right? Something it is coming, right? 0.25 divided by 193 plus 0.75. So 75.2129. Okay. So you are getting 75%. Right. So how many processors you can execute? Based upon that, you can make a conclusion. Right. Like here you can see in comparison to this one, 256. If you have less number of processors, it is better. Again, if you try with only 100 processors, okay, let's say 100 processors, then 0.25 divided by 100, 0.25 divided by 100, okay, plus 0.75. So you're still getting 0.75 only. So with lesser number of processors, it is better, right? So what is the conclusion here? You can see earlier you got the efficiencies only the previous one. If you calculate the efficiency you got only 1.5%. But in this case, the efficiency is increased to 0.751. That's why what we can conclude here, the main conclusion is that if there is a fixed workload, you can go for Amdahl's law. If there is a scaled problem or scaled workload, you can follow the Gustafson's law. In this way, you can calculate. Another set of performance matrices that is also used to calculate the performance, like especially if you want to know what is the availability of a system. Okay, availability of a system. In order to calculate the availability of a system, there are some factors that you need to calculate. Okay, like one of the calculator for this one is called as mean time to failure. Similarly, mean time to repair. Another is called as mean time between failure, which is not given here. Okay. So suppose a failure occur. See the relationship between these failures. Suppose there is a failure occur. Let's say this is my first failure. You start a system here. This is your first failure. Okay. So once a failure is encountered, you have to repair it. So you start the process of repairing this particular failure. Okay. So once you start repairing, then let's say the repairing is done at this particular period of time. You started solving that particular failure. Like system crash happen, you start repairing a system, and this point of time it is completed. Now, after fixing your failure, you continue, you encountered another failure here. So this is your first failure, this is your second failure. So the difference between two different failure is called as mean time between failure. Right? And when you start a system and encounter the first failure, so this is the correct behavior, right? Or the system is working smoothly. So this correct behavior is called as mean time to failure. That is when you start a system till first failure. Right? This is the parameter, MTTF. Again, you can see a MTTF here. Because you have solved the problem here, your repairing is done, again you encountered a failure here. Right? Now, how much time is required to repair this particular failure? It is the difference between the end repair and begin repair. That is called as mean time to repair. And what is this time? This time is called as mean time to diagnose. Once a failure is happened in your system, you have to diagnose it, right? Once diagnosis is done, then only you can start repairing. So, in order to find the system availability, what you have to do? You have to do MTTF, mean time to failure, divided by mean time to failure plus mean time to repair. That will give you availability of the system. Right? The given data, you can calculate it. For example, I'll tell you that over 10 hours time, okay, a system is running smoothly for 10 hours. After 10 hours, let's say there is a failure. And diagnosis time is, let's say, 30 minutes. Repairing time is, let's say, 1 hour. Calculate the system availability. So mean time to failure is 10 hours. Mean time to failure is again 10 hours. Mean time to repair is it is 1 hour. It is not the diagnosis time, right? Okay, diagnosis is not going to be considered. Okay, if you consider the whole is mean time to repair, if you consider diagnosis is a part of mean time to repair, then you have to write 1 hour 30 minutes. In fact, diagnosis is also a part, so you can write 1 hour 30 minutes. So you have to calculate 10 hours divided by 11 hours 30 minutes. So that will give you system availability. Okay, and you have to ensure that there is no single point failure in the system. There should not be any kind of single point of failure, just like a, you can say, centralized system. So the rule of thumb says that dependable computer system with no single point failure. Systems are coordinating each other to execute a particular application or to perform a particular work, but there is no single point failure. So if you go for cluster, like I told you, a 256 node cluster, 100 clusters, so it is high availability with fail over capability. Fail over capability means once you encounter a failure, let's say secondary is treated as a primary and primary is treated as a secondary. Okay, like whenever systems are having redundant systems, right? If a system is failed, another system is coming to picture so that it can compensate the work of that system until unless the system is recovered from the failure. And with respect to the different kind of system, if you compare the performance of the different type of system like cluster, grid, symmetric multiprocessor, non-uniform memory access, okay, the different architectures are there. So you can see their comparison with respect to the number of cores and system availability. So cluster and grid case, you will find if you increase the number of processor cores to a larger number, again the system availability is increased, right? But if you see the symmetric multiprocessor, its system size is also small, means number of cores are small, availability is also less. NUMA architecture case, number of processors also small, system availability is better than SMP, but not better than other type of systems. Like that, you have several systems. You can compare each and the other system and calculate their system availability based upon the number of cores varying in a particular range. Okay, we'll stop here. If you have any questions, you can ask.